Hey everybody. So today's lecture is going to be relatively short. We're going to go over some of the concepts covered in our very first lecture in more detail related to the research process with a focus on sampling. Before we get into that, I have an administrative announcement. Both the quiz and homework assignment for this week has been posted to Canvas. In addition to those two regular assignments, there's a third assignment posted, which is the research question you want to investigate for your final project. And there's some associated questions in there for you to answer. It shouldn't take very long to fill out. Really, the bulk of the work is to look at the questions and think through, find a topic, something that you'd be interested in researching further, that you might be able to do in the scope of this class and applying the concepts we've learned in this class, which we will cover today when we talk about the overview of the research process. From there, we'll move on to sampling and potential biases to watch out for when you perform sampling or if you are involved in the data collection process, which is not always the case. Sometimes you receive the data in advance. So to start, this isn't like a hard and fast guideline to the research process. This is just some suggestions that I came up with looking at other people's explanations of the research process. I broke it down into 5 pieces. So the first of those is planning. I think this is often overlooked, but it's a really important part of your research because there's an old joke that a tech lead I had used to make, which is that hours of coding can save you minutes of planning. It's kind of a lame joke, but obviously it's a joke because you normally think about it the other way around, which is that minutes of planning can save you hours of work. So it is really important to plan what you're doing, because especially when it comes to data collection, if you collect the data improperly, it makes the rest of your research kind of moot. And as I shared in our first lecture, I've heard of this happening many times over at SAGE, the statistical consulting group at Virginia Tech, where people will come in with weeks to submit their research, sometimes days, and they'll share their data, and it turns out it was incorrectly collected or formatted, and there's really not a lot you can do at that point. So it is important to spend time on planning, and that's what you're going to be doing in the third assignment of the week, which again is meant to be brief. I know it seems a little overwhelming to have 3 assignments due in 1 week, but this is really just thinking about a research question that is of interest to you. Then you want to identify the population and variables of interest, which will inform the sorts of data you're going to collect. And then when you design the data collection process, which may involve conducting actual experiments, there's a golden rule that the professor for experimental design taught us that I think summarizes really well the principles behind design in a simple way. And that is block what you can, randomize what you can't. And we'll go into more detail of what blocking, also known as stratification, is and what randomization is when we get to sampling later on in this presentation. After you've created your research plan, you'll perform your actual sampling, which can be through experimentation or collecting data through surveys and other methods. Then we talked a lot about exploratory data analysis. That was really the subject of the first homework assignment you guys submitted. We talked about univariate analysis, which can be in the form of descriptive statistics, or graphics and plots such as bar plots, pie charts, or donut charts. For categorical data or for quantitative data, you really want to stick to those 5-number summaries, or you can use box plots, density plots, or violin plots or histograms. Then there's bivariate analysis, where you're looking at the relationship between variables, where you have many more options available to you. In the case of quantitative data, you'll use scatter plots. In the case of categorical data, you don't have a ton of choices either, but there's two-way frequency tables, mosaic plots, which are really just very similar to two-way frequency tables, might be more appealing to some visually. I never found them as easy to understand as the two-way table. And then there's categorical and quantitative variables where you can look at things like side-by-side box plots, overlying histograms, overlying density plots, and a few other graphics that we've discussed. Now, these last two steps we haven't really covered much in class, which is inferential statistics, which we'll get to in time before the end of the semester. And then you want to conclude by recommending next steps in pursuing your research question further for future analyses. So let's talk a little bit about sampling. So I put what I think are the two most important techniques and approaches to sampling first. So randomization is a relatively inexpensive or cheap way to not guarantee, but somewhat guarantee that your sample is representative of the population. That's because, as you know, if you pick randomly and your sample size is large enough, eventually you are going to get something that looks like the population. There is a small chance that you pick randomly and you get something that looks nothing like the population, however, and that's known as sampling error. And there's not a ton you can do about that besides increasing your sample size. The second approach, however, helps to avoid sampling error without increasing your sample size, and this is known as blocking or stratification. We talked about this in the first lecture, but the idea here is that you think of groups that exist in your population, and you make a note of the proportions within those groups and mimic that within your sample. So the example I used when we first talked about this is men and women might have a different opinion on an issue. So in your sample, you ensure that you have an equal number of men and an equal number of women, assuming that your population is 50-50 men to women. Because as you can imagine, with randomization, you could wind up with all men. It's unlikely, especially as your sample size increases, because we know the population is roughly 50-50, but it could happen. Whereas with blocking, you're avoiding that possibility by saying, I am going to ensure that I pick, if my sample size is 10, 5 of them are men and 5 of them are women, and then I'll apply randomization within those strata or blocks. A couple other approaches. There's cluster sampling, which is not as powerful as randomization or blocking, but can be more convenient. So the idea behind clustering, and I've seen this happen many times. Last semester I taught a CMDA capstone, and they wanted to learn about the opinions of college students as it relates to using AI in their homework. It would have been difficult and expensive to interview students from colleges outside of Virginia Tech, but it was really easy to interview students within the program, and that's what they did. That's an example of clustering, where you look at one specific cluster, you sample from that cluster, and you assume that that cluster is representative of your larger population, which is not always the case. Systematic sampling, on the other hand, is closely related to randomization, but instead of picking randomly, let's say, your population consists of 100 people, which is very low for a population, but just for the sake of this example, I'm going to say your population is 100 people, and you have the budget to study 10 of them. You would make a list and pick every 10th person. So as you can imagine, there's overlap with this approach and randomization. If you assume that the order of the list is independent, you wind up with a somewhat pseudo-random is the word that's used, but a somewhat random sample without actually using a random number generator or anything like that. And then there's convenience sampling. So this is when For example, you give a survey to people as they complete, like when a store gives you a survey at the end of your transaction, right? You're there, it's convenient for them to ask you, and they might even give you some kind of incentive for you to fill it out. This is very likely going to result in biased data, which is okay if you qualify it, right? If you qualify that this data is biased and is this is the types of people in the sample and how they vary from the population, so you're only going to do inference on these types of people, that's fine. But you do need to qualify any limitations in your approach so that people aren't incorrectly making inference on a population that looks nothing like your sample. So we talked a little bit about sampling error, which is going to happen inevitably. And your goal is really just to minimize it with these approaches like randomization or systematic sampling and blocking, also known as stratification. Those are some common proven approaches to minimize sampling error. There's also non-sampling error, and what people mean here is this is error due to the design of your experiment. This is error that could have been avoided if you had designed your study in a different way. So you should have none of these kinds of errors. And I'm giving you 3 examples here of how they could occur. There's the design, which we mentioned before. I'll give you a quick example of a non-sampling error. If I want to know the outcome of an election, which is an example we've used in this class before, and I were to use cluster sampling on people at Virginia Tech, I'm very likely going to wind up with a biased data set that does not represent the opinions of the nation as a whole. There's a lot of reasons to believe that students at Virginia Tech will vote differently proportionally than the nation as a whole. First of all, it's a college. It's located in Virginia. The demographics are different than the population as a whole. It's definitely younger on average. It's probably, I don't know if it's more or less diverse, but my guess is more diverse than the nation as a whole. So this is, really problematic. And these are the kinds of errors that are not inevitable, and you should design your experiment so that you're avoiding these errors. Undercoverage is related to not sampling enough people. So as I said, with these approaches like randomization, as your sample size grows, it looks more and more like the population. However, if you don't sample enough people, you could wind up with a sample that doesn't look like the population, and we refer to that phenomena as undercoverage. And then there's errors in your actual analysis and the way you carried out the approach, and these are the way you carried out the analysis. And these are unfortunately quite common in the social sciences, and this is something that really needs to be addressed, and hopefully we'll cover in much more detail when we get to inferential statistics. The idea is you have to choose the right tool and the right interpretation to reach your conclusion so that your results are both reproducible and understandable in terms of their limitations towards people who read your analysis. All right, lastly, we'll go through some examples of bias. These are just things to watch out for. This list is far from exhaustive. There's a lot of reasons that you sometimes wind up with biased data. I'll give you some of them. If you're asking people very personal questions that they don't want to answer, there are privacy concerns, and they might give you answers that are untrue. Similarly, especially when there's an incentive, people might just be rushing to get through the survey, and they're not taking their time to thoughtfully answer their questions. Incentives themselves are a kind of bias. Like, you might remember some fast food restaurants on your receipt will say, give us a survey, tell us how we did, and we'll give you a free meal or a credit off your meal or something along those lines. So people are filling out those surveys for the incentive, and you can imagine there's a kind of bias in who's motivated by that incentive, right? tend to be lower income people who are going to be motivated by low dollar value giveaways. And as you increase the dollar value of the giveaway, you may get a somewhat more representative sample, but it's still going to be the case that there are people who are like, it's not worth my time. Also, the actual questions you ask can be leading, and that happens a lot. You might hear about people using statistics to misrepresent the truth with leading questions. One example that I remember is the wording of how people refer to the Affordable Care Act. So when they called it Obamacare, the responses tend to be more negative than when they refer to it as the Affordable Care Act. Now, I wouldn't necessarily say that's a leading question. That's just a bias to be aware of, that some people will view it differently based on how you word it. A leading question really refers to something that's intentionally trying to guide your answer in a certain direction. Another type of bias is misinformation. People just don't know that they're giving you inaccurate information. They might be unaware of the truth. And then the last example I list here, which we've talked about in the past, is when you have self-selected or voluntary samples. You might have heard of negative response bias, is a real thing. So like when you have reviews or ratings, those tend to be polarized. Because if you have an average experience, you're less likely to leave a review than if you have an amazing or awful experience. The conventional wisdom years ago was that the people who have extremely negative experiences are most likely to leave reviews, and that's where that term negative response bias comes from. But we actually know that both are true. Extremely positive experiences also lead you to be more likely to leave a review than an average experience. So these are some kinds of examples of bias, and it's important that you're conscious of where bias may be introduced in your experiment. And we talked about that golden rule in the design of collecting your data. Block what you can, randomize what you can. So thank you very much for your time. I know this lecture was a little short. We did cover most of this material early on, but I wanted to review it, and I will see you tomorrow.